inequality and Chebyshev's inequality, which are two of the most fundamental inequalities in probability theory. Markov's inequality is used only for non-negative random variables. This is a very important point to note, and it states the following result. The way we go about proving this is using the standard expectation formula here, uh, here, and since we want k as a parameter in the inequality, we introduce k. We separate this into two separate uh, summations according to the value of the range of a with reference to k. Once we have done this, since we want a greater than equal to sign here, and we want probability of x greater than k, we will keep only this term and neglect this term. So expectation of x is greater than equal to this term right here, and since a is greater than equal to k, so we can take this k out of the summation. We can put it here as well, so like we've done here, and then the summation, once we have k outside, then the summation, then this particular summation, what this basically means is that we are calculating the sum of probabilities of a which are greater than equal to k, which is the same as this, and which is what Markov's inequality tells us by shifting k to the denominator. So this Markov's inequality. Chebyshev's inequality, the important point to note is that while Markov's inequality was true for only positive non-negative random variables, Chebyshev's inequality is valid for any random variable. The statement is this, and the derivation is pretty simple, where we expand, we equate this probability to the probability of square. So if a is greater than b, this implies a square would be greater than b square, where if obviously if a and b are positive integers, so are positive quantities, then these two statements are equivalent. So inducing this equivalence here, and then we prove, so this we consider this mod of x minus e of x to be a random variable y. So we are interested in finding the probability of y square is greater than equal to k square. Now y square is in itself, let's call it z, and it's in itself a positive, that is a non-negative random variable. Hence we can use the Markov's inequality as we have done here. Now variance of x can be calculated as this. Expectation of y square is nothing but the variance of x. So probability of y square is greater than equal to k square is nothing but the variance of x by k square. And from this equivalence, we can conclude that the probability of y is greater than equal to k is less than equal to variance k by k square. This is our Chebyshev's inequality. Now what this means in practice is that see, Markov's inequality is, it basically gives us a bound on the probability that a certain certain non-negative random variable does not exceed its expectation or exceed a certain quantity by a large amount. It will give us a bound that what is the probability that a non-negative random variable is greater than a certain quantity, certain threshold. It will give us an upper bound on that probability, right? This is Markov's inequality, while Chebyshev's inequality is, first of all, it doesn't have any inbuilt assumption. X can be a non-negative as well as a negative random variable, anything. And Chebyshev's inequality gives us a bound on the probability that a random variable is neither too is not too skewed. So it's neither too big nor too small. So it gives us a probability that the random variable lies within a certain distance from the mean of the random variable. So and the probability that it lies outside a certain distance from the mean on both the sides is bounded by a certain upper bound. So this is that particular upper bound. And we use Chebyshev's inequality and Markov's inequality extensively in probability theory. Thank you.